Well, we were talking about bandwidth theorem in previous lecture, and now we want to prove it for bipartite graph. The proof for non-bipartite graph is similar but a bit more technical. So we will prove it for the bipartite graph and then leave the generalizing into more K-chromatic graph as an exercise for the audience. So for given delta and alpha, there exist eta and 0 such that the following goes. Or larger than n 0 and larger than n 0. In other words, we assume that like you can simply write it this way. But anyway, so this is what we mean. So if H is an n vertex bipartite graph with the bounded maximum degree, which is also eta separable. We defined this separability last time. Eta separable means that you can take at most eta n vertices and delete it, and rest of the vertices, all the components have size at most eta n. And many natural class of graphs are eta separable. For example, planar graphs are always eta separable for small number h, arbitrary small number h, as long as your planar graph has sufficiently large number of vertices. Or any graph from a non-trivial minor cross family also satisfies this. And yeah, etc. There are many natural classes of graph which which contains all the graphs in that class is eta separable for arbitrary small number eta. And if G is an n vertex graph with the minimum degree, it is half plus alpha n, then G contains H as a subgraph, spanning subgraph. In other words, H embedded into G. So we want to prove this. So let's assume this. So we know this, and we know these are sufficiently smaller than that. So we can so this is for the existence, so we can choose n0 so that which is much bigger than eta. That's no problem. And we know that the eta is much smaller than these. So in the middle, we can choose some numbers. This is much smaller than these two, and then alpha epsilon is much smaller than d, and 1/m is much smaller than epsilon, and then still eta is so smaller than that, so that this is much smaller than any of that. And these are actually, we can write down as an explicit function. So this is f of these two, smaller than f of these two for certain f. And this is like g of smaller than g of d for certain g. And then we can specify this f and g and other function, but that's like tedious and technical, so we will not do that. So first, what we do, we apply the regularity theorem. to G with, say, parameter epsilon and M, then what? We obtain an epsilon regular partition B0, B1, BR with R being smaller than 1 over M, which is given by the regularity lemma, but eta is so smaller than that, so that this 1 over R is still, this eta is still much smaller than 1 over R. If you want to do it more formally, you can take like M prime here, and you can find its partition with the R being at least M and M most M prime. So that's what you can do in the regularity lemma. In that case, this has the same effect. We know that this happens, this holds. So we might as well just write it here. But formally, at this point, we don't have a parameter R yet until we actually apply the regularity lemma. So, it's better to write it, say, this way. This is more rigorous. Now we have this epsilon regular partition, and we consider the epsilon D reduced graph R on the vertex set R. Okay, yeah, I forgot to mention one. Maybe, we assume R is even by moving vertices in BR to B0 if necessary. Meaning that if R is odd, then you take the last one and you move all the vertices to B0, and you can reduce the R by 1. Then you can assume that R is even, and B0 still have a size at most 2 epsilon M. So this is pi. And let M be the size of each pi. So all of the pi here have the same size. And this M is like, you know that this is roughly N over R. And we know that the alpha is bigger than D, so as alpha is bigger than, say, 10D, we have, so there are some exercises we have before regarding this regularity. One of them is once you take a reduced graph, then that reduced graph inherits the minimum degree condition of the entire graph. It's reduced a little bit, but not too much. It's reduced by some constant times D and constant times 1 over R and etc. So essentially you have this minimum degree condition. So by Dirac's theorem, what we know, if R contains a perfect matching. So assume that it is the R prime, which is 1, 2, 3, 4, 5, 6, R minus 1 R. So by re-indexing, giving different indexes, you can assume that this perfect matching is like 1, 2, 2, 3, 1, 2, 3, 4, 5, 6, and etc. And for our convenience, for each vertex I, for each number I, let I star be its counterpart, its partner, unique number in R such that I and I star are paired up in this perpendicular. So 1 star is 2, 2 star is 1. Okay, now what we have? So we have this P1, P2, P3, P4, P5, P6, and we know that they are epsilon regular. Our plan is to somehow make it epsilon superregular, and then you prepare your H. So this is G. This is your G. And later we also prepare your H in a way that you also partition them into these sets. And then you invoke block lemma to embed it here. And while doing that, some of the small number of edges may go between, but we want to make sure that most of the edges are here and here and here. And we use this epsilon regular partition to embed it. Before doing that, maybe you have to take care of this small number of edges first. So that's roughly our plan. And for that, we need to make sure that these are epsilon superregular. They have to be equipped with minimum degree condition. So first, we want to ensure that. How? So let m prime be some number which is like smaller than the size of its bi, but not much smaller. And one of the exercise, I mean, in lecture note, it's currently the currently numbered as a 3.4. What is it? So essentially, so maybe we know that if you have a epsilon regular partition, and then you have certain m prime, which is between, which is not too small and not too big. So it says size, say m. Then what you can do is that for any m prime, which is between, say, 1 minus 2 epsilon m, 1 minus 3 epsilon, like 10 epsilon m, you can choose a set of size exactly m prime with exactly m prime, and you delete this, and then you can make sure that this set induces a superregular pair. In fact, this upper bound is here because there could be some small number of vertices with low degree, so you have to completely delete so that this cannot be too high. Once you delete it, then now you can freely delete a bit more vertices until you have exactly same number as you wish. So by using this exercise, so it's left as an exercise in the previous lectures, and it's also in the lecture note. We can find the that's UI subset of PI such that each UI has size exactly m prime, and each UI comma UI star is, say, 6 epsilon G plus superregular. So this is 6 epsilon regular with a density bigger than D, and the minimum degree is at least like D over 2 times n m prime or something for all I. And we move all vertices in which is not included in UI into this B0. Then what? It's B0 as size versione. Okay, so now what we do? So this is some problematic vertices. We have to, in order to embed H into G, we have to use all the vertices in G because they have the same number of vertices. So if there is some vertices in V0, that's problematic. So we want to distribute them into the correct place. So we wish to distribute the vertices in V0. How do we do it? For each V in V0, what do we know? We have that its degree is at least r plus alpha times n. Then what? Then this implies that there exists at least r plus say alpha over 2 r indices I such that it sends at least d times m prime edges towards ui. This is true because otherwise what? Let's say you have V and then it's sending many edges to here, many edges to here, many edges to here. So say at most r plus alpha over 2r vertices, it sends full number of edges, so as much as possible. But still, this is like smaller than its degree minus alpha over 2n. So this alpha over 2n edges has to be distributed here. By Pigeonhole's principle, at least one of them must get at least alpha over 2m edges, but these, that's already bigger than Tn. So we can show that there must be at least this many indices I satisfying this. So in such a case, if we add this V to say ui star, so you have ui star, and this V has many edges here. Then if we add it to here, then what do we know? ui star is still superregular. But maybe with very slightly worse parameter. Because it still satisfies the minimum degree condition. And epsilon regularity condition is not disturbed too much by adding this one vertex. Or even if you can add like very small number of vertices, its epsilon regularity condition does not deteriorate too much. It gets slightly worse. The epsilon may become a bit bigger, but you can still ensure that it's sufficiently small number. So with this purpose in mind, we distribute the vertices in V0 into sets u plus 1 to u prime 1 to u prime r, such that the following holds. So say u prime 1, the first property is that for each I and p in this u prime I, we add this vertex to u prime I only when it has many neighbors in ui star. Otherwise, we would not add it. So we will add this u prime I to ui and then take a union later. And while you're doing that, so you will add it add some number of vertices u prime I star and u prime I. You want to make sure that after adding it, it's still superregular with slightly worse parameter. And for each I, we ensure that we have that this u prime I as side and we'll say 10 times epsilon, B0 divided by alpha R, which is like most say epsilon to the 1/2 m prime. And third, for each I star in this matching, we had that their size is almost same. It's either same or difference is at most 1. Okay, we claim that such a distribution is possible. Why? You can greedily add HB in B0 to 1 of U1. And how do you do it? So we observe that it's B, that means it stands like that many indices such that this holds, right? This is more than half. That means in this matching R prime, there are many things, many pairs, both of them receive many edges from this B. So this has at least say alpha R over 2 indices I such that this holds. And the both holds. Then what? If there is such an index with say u prime I is smaller than u prime I star, then we add say we add this B to the smaller one. If the previous one was still satisfying all three properties, now after adding one, none of them stop holds. So all of them still holds. So this one is fine by our constructions. And this is still okay. So you add one vertex to the smaller one. So this will never break. And then this is still okay because the I star, UI star is bigger than UI. And then UI star already still satisfies this. So after adding one, this one is still okay. Because U prime I is smaller than U prime I star. If not, then there are these many choices and all of them have the exactly same size. Then we choose I with whose size is smaller than this. This exists by Pigeonhole principle. There are this many indices. And we know that if we add up all the sets, U prime I all together, then their total size is smaller than B0, size of B0, because we are distributing B0. So this holds. And we add B to this B prime R. And actually this is strictly smaller because B is not yet assigned. Then, this holds. So you can ensure that you can make a distribution that this holds. So this number here is actually bigger than here. But this 10 was not typed. We could write 2, but I just wrote 10 to be safe. And now we define our U star I as a UI union with U prime I. And let's say Ni is the size of this UI star. Okay, then what do we know? So initially we have this UI and UI star. They were, say, 6 epsilon T plus superregular. And then we added this U set, U prime I. All of them has a large minimum degree into here. Then, by using one of the exercises we have shown before, you can add or delete some small number of vertices, then the epsilon regularity is essentially preserved. Of course, the number gets a bit worse, but that's okay. So, by using that exercise, we have the following. So, they use star 1 for each I star in this matching. The pair, they use star I and use star I star, is still, say, epsilon to the 1 over, say, 5, it plus superregular with Ni being Ni star plus minus 1. So they are almost same, 4 by 1. And this Ni is more or less like 1 plus minus. This is much smaller than, this is much smaller than epsilon to the 1, epsilon to the half. So let's just say this is 1 over quarter. And if we write it here, then let's write that's 1/5 to be safe. And this is more or less like this. Okay. So now you have some tentative partition of G. So what you have in G, you have U star 1, U star 2. This is superregular, U star, superregular, superregular, superregular. U star R minus 1, U star. Now what you want to do is you want to prepare H. You want to partition H in a coding way so that these are independent sets, and most of the edges are between, and small number of edges may be between. And we want to make sure that this has the exactly same size and exactly same size. That's very ideal situation. However, that's too much to hope for to make it exactly same size. So we first aim to partition H in such a way that this size is very close to here. This size is quite close to here. And this size is quite close to the size of this, and etc. So now our goal is to partition H accordingly. so that each part has size very close to this NR, so which is size of this. So how do we do this? Of course, we use the separability. So using separability, yeah, before using separability, this is bipartite graph. So let the A1, A2 be the vertex partition of H into two independent sets. And using separability, we can partition this vertex of H into W0, W1, dot, 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 WT, so that for each of them is small. So all of them has size at most 8 times. And also another property is that for all S, which and S and S prime, both are non-zero number, and that they are different, then H has low edges between WS and WS prime. So essentially this W0 is the separator, and W1, W2, dot, 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 WT are the components. And T is at least 1/8 times at most, say. An over 8. So you take W0, and if W0, which is separator, if this is a small separator, and then you get this component. And if, okay, and some of them, note that every one of them has size at most 8 times. But we want to make sure that this is T is not too big. So if some of them is too small and another one is too small, then we might want to take a union of them to take as WI. Because we only care about these conditions, so that's fine. And also if this is too small, then we might add one of them to here. And you can take this as a separator. That's still fine. Anyway, by doing that, we can ensure that this T is between these two numbers. So we have this partition. Now, what do we know? Due to this, all edges are either you have this W0, W1, W2, dot, 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 WT, and all the edges are either between W0 and WI or inside here, inside. Why does it get deleted? So for each S, which is either 0 or number between 1 and T, let WS, 1 be WS intersection with A1. So the number of the vertices in WS, which is colored with the first color. So this partition A1, A2 is a two coloring of your graph. And WS2 as a WS intersection with the second color. So now what? We have these small pieces. Now we want to group them. We will partition this W01, W02, W11, W12, dot, 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 WT2 into collections. They curly W. 1, 2, curly W 2, 2, curly WR. Which we partition them in a way that they satisfy the following. So for say all I and I star in this matching R prime, and S, which is bracket T and 0, and L between 1 and 2, if this WSL is designated in curly WI, then its counterpart. So if L is 1, then 3 minus L is 2. If L is 2, 3 minus L is 1. Its counterpart is assigned into the counterpart, the curly WI star. And second property is that for all I, what we have is that if we take all W, which is assigned in this curly WI, then we add them, we count the number of vertices in there, and that's roughly very close to Ni. So what was our goal? Our goal was somehow partition your H in this way so that here the number of vertices is very close to N1, and here the number of vertices is very close to N2, etc. And then what we want to do is we take this partition curly W1, and in there, I mean, we have this W1, 1, and W, say, 5, 2, etc. We will assign that to here. This, we will take the union here, and it will have a roughly same size as Ni. So, this is what we do. Indeed, this is possible. Indeed, such a partition exists. To show this how we do it randomly. So for each S in this T, so W0 we will not assign yet, but for other one, what? We independently at random choose a number I, in this say R over 2, such that what? This is chosen with, say, probability n sub 2i plus 1 plus n sub 2i divided by n. And we choose L, which is either 1 or 2 with a probability half. What you do is if L is like, so this is a random event so that each I is chosen with this probability, and you add up all the probability to be chosen from 1 to R over 2, and they sum up to 1. So this is a proper, I mean, this is a proper random experiment. If L is 1, then what? We add this WS1 and WS2 to this curly W2I1 and call it W2I respectively. If L is 2, then we add them another way, the other way, to curly W2I and curly W2I minus 1 respectively. Okay, then what do we know? Then expected size of each, Wi is what? It's like half times n I plus ni star over 2, not 2, over n. It's roughly what? That times, that's the probability, and then you have to add or wi, I is 1, 2, t, right? And this is roughly n minus eta n. So this is like 1 plus minus eta times n chi. So the expectation is very close to ni. And this is not exactly n because W0 we are not assigning. But it's not too big deal. Then we have this very close expectation. And then we want to claim that the concentration falls, meaning that with high probability, this number is very close to its expectation. In fact, there is this weighted version of Chernow bound. And suppose that you have x1 to say xn are independent random variable. Such that each xi takes the value in some interval of real number of length, say ci, which before in Chernow is either 0 or 1. And there are some probability. But now this xi could have some value, but the maximum of its value and minimum of its value are different by MOC. So maybe in such a way that it's better to write it this way. Maximum possible value of xi and the minimum possible value of xi is MOC for some number set. And let x be the summation of xi. And the probability that x deviates from its expectation by more than t is almost 2 times e to the negative t squared divided by 2 of summation of ci squared. So this is Chernow bound for like weighted version of Chernow bound. And there is something called Azuma's inequality, which works for martingale. And then this can be considered as a special case of Azuma's inequality. And by using that, what do we know? Here, what's this ci? So here, for each f, we either add these sets to here or not. So, this number plays a role of, this summation of ci square. But we know that this is at most like this is at most eta n square. So this is at most eta n. This is at most n. So we know that. So we can apply this theorem. Then what? the probability that this holds is that by this weighted version of the Chernow bound, the probability that this second property holds is at least 1 minus there are many events 2 times e to the negative eta 2 over 3 ni squared. So ni has size at most n, so let's say n squared divided by this one. So times 2, so 2 eta n squared, no, 2 eta n, yeah, squared is what? 1 minus 2r e to the negative 1 over eta, say 1 over 4. And eta is small enough so that the eta is much smaller than 1 over r, meaning that the 1 over eta is much bigger than r. So this is actually at least 0.99. So with positive probability, which is very zero. So there exists a partition, this random partition that satisfies this curly W2 and also curly W1 as well. Because what is the curly W1? If one is assigned here, its counterpart is assigned to its counterpart. That's obvious from how you assign this two. You choose this L, you assign either here in this way or in this way. So this to here and here, or this to here and here. So this first one is okay. Now, yeah, I was a bit long when I say we don't assign W0. We do assign W0 as well. So for each sim as well. Sorry. Then, yeah, this one is actually more close. This is N, so this is more like very close. Okay. Then, yeah, now W0 is assigned somewhere. So by permuting indices, if necessary, assume that the W01 is in curly W1 and W02 is curly W2. Okay. Yeah. Now what? Let's say W star I is the union of all things that's assigned that is curly Wi. So you have this U star 1, U star 2, etc. And then you have this like W star 1, W star 2, etc. And we want to embed it to here and it to here. There are certain problems. They don't have exactly same size. Roughly same size, but slightly off. That's one. And also, what you have now is the following picture. You have a W01, W02. And rest of them are well distributed so that the edges are here and here by the W1 property of curly W1. But the edge between here to here, I mean, there could be even edges to here as well. These edges could be arbitrary, so that these edges have to be embedded to here. That has to use some edges other than this superregular part. Remember that in H, the edges are all between either inside each Wi or between W0 and Ws. So W0 is here, so you might want to use some edges here. Okay, so we need to further modify this partition. What we want to do, we want to assign vertices to xi and yi. So most of vertices will be in xi and very small number will be in yi. And xi are the vertices which are kind of good, so that between xi and xi star, they will be embedded into G using this superregular part. But y are some small exceptional one. We will use some other edges in G to embed into. And this y will be the ones that's incident with these edges. So y will be the vertices which are close to this W0. So what do we do? So we assign vertices in this W01 to Y1 and vertices in W02 to Y2. And now we consider each F and I and assume that its WS1 belongs to curly Wi and WS2 belongs to curly Wi star. Then what do we know is that we know the R. So here, these are like R prime. But in here, we have actually R in graph, in this reduced graph. So in G, there could be more edges between, which may not belong to any superregular pair. But in order to use that, I mean, that's information is encoded in R. And this R has large minimum degree. So in R, you take 2 and I star, and then you consider their common neighborhood. And there are at least dr common neighbors of those two. 2 and I star in this R. Then what? We can find the following index, say Q of S, satisfying which is a common neighborhood, which in here. So there are this many choices. So you make one of you choose one of them. And in G, what happened? You have it's U star 1, U star 2. This is superregular. Then U star I, U star I star, which is superregular. And then you take a U star Q. Then this is superregular, this is epsilon regular, and this is epsilon regular. So these are superregular, and these are only epsilon regular and epsilon regular. And this is picture in G. In H, what we have is you have assigned. So here W01 is assigned, W02 is assigned, and WS1 is assigned, WS2 is assigned. So here are collection of the vertices in curly WI, curly WI star, curly W1, curly W2. Then what we have is that maybe let me draw this in a bigger way. WS1, WS2. And this set might have some neighbors here. This has some neighbors here. And then they might have neighbors, neighborhood, and neighborhood. Okay, what we do is that we want these edges to respect the structure here. So these edges are not good because we don't know whether there are epsilon regularity between here and here. But these are crossing. So what we do is we take YQS and then we assign some vertices here to here so that this edge structure become respecting this structure. So what we do? We first assign all vertices in H, the neighborhood of W01 in W02 to Y2. So WS22. Sorry. So here, these are these vertices. So we move these vertices and we will assign it somewhere here. As a part of Y. So this will be there. Then what happened? These edges and these edges will change so that it's going to here and here. And now still these edges are problematic. So what we do is we assign all the vertices in W02 neighbor in H, which is intersection with which lies in WS1, as well as WH2 in W01 in WS1 to YQS. So all of these to YQS. What it means? The first one is when we have this and then you take the neighborhood, so this set. So we move this set to here. Then what will happen is that this will be gone and they will be connected here. And this will be gone and they will be connecting here. As well as the second one, the neighborhood of W01. Its neighborhood are all here and its second neighborhood are all here. So this will be also go here. So what? Here and then right here. So after doing that, what? Now this structure respects structure here. The edges between here are all gone. So we do this. And we do that for all choices of S. For each S, there is specific I that this holds. And then with that choices, you can choose this and you do that. Then after doing that, what happens is that if there exists an edge between y, say y I, and say y j union x j. So as we did here, so this respects the structure here, means that all the edges between here and here and here are either between y2 and yqs, or x2 and y2s, yqs, or here it's either from y or x, it doesn't matter, and it's from yqs. So between yi and then some other thing, then this ij is in R, and if there exists an edge between, yeah, I didn't say what's in X. So we do that for thing, and we say assign all the rest vertices. Rest of the vertices in WS1 to XI and WS2 to XI stop. And also, if there is an edge between XI and XJ, then IJ must belong to this matching, because X are assigned in a way that between X, all the edges are here, so it corresponds to the tuple regulars. So now we have that. So now what? But what we know is that every vertex in Y, I, is distance at most 2 from W0. But what we know is that the maximum degree of H is at most delta, and we know that the W0 has size at most eta n. We have that each yi has size at most 2 delta square eta n. Then what? For each I, we let n prime I be the size of union of xi and yi, which is the one that we will assign. Then what do we know? We have from right this curly W2 shows that its summation is this much, but some of the vertices were kicked out to go to be assigned to be in some of yi. So it's altered, but the number of vertices altered is at most delta square eta n, because they are all different 2 from W0. So this is almost this plus some altered. So this n prime I is 1 plus minus 1 over eta to the 1 over 4 times ni. Now we have the good situation. We have not good, but okay, better situation. X1, X2, X3, X4, X5, X6, and you have like superregular, superregular, superregular. And then some Y1, Y2, y3, y4, y5, y6, and some of the vertices, this small number of yi is maybe problematic, or the edges between xi are in the right place in this edge, while there is small number of vertices yi, which may contain this irregular behavior edges. However, if there isn't this edge, let's draw red to indicate superregular. And if there is this edge, then there is epsilon regularity between this pair and epsilon regularity between this pair. So this is situation, and they have almost same size, but not quite. So we are in a better shape, but still, I mean, we want to make sure that this size and this size is exactly same. How do we achieve that? Making further modification in here is not good because H has less flexibility, but here we have more flexibility. For example, if we move one vertex to somewhere else, I mean, if you do it carefully, then the superregularity and epsilon regularity will not be ruined. So now we turn our attention into G again. So this is our final partition of H, but we'll make further modification on this partition. So this is almost correct. Now we will make some more partition to make sure that this has exactly same size as this. And yeah, maybe it's good point to break this video. So in next video, we will start, telling about how we make a further modification on here so that the this has currently size what ni, and this has size like n prime I. We'll make further modification to make it size exactly n prime I. And then after that, our plan is to embed this yi, which is in here first, which is small, so which is relatively easy. And once we do that, some of these vertices are embedded and their neighbors. So if, let's say, this vertex is embedded to here, then what? This vertex has to be embedded into its neighborhood here. Because this is epsilon regular, you can embed so that it has large neighborhood in here. Then later when we invoke our blow lemma, we make sure that this one is embedded to here. That's possible. One of the additional property of blow lemma is that if you have a small number of vertices and each of them has some target set that we want to embed it into, then you can find the embedding that satisfies such restriction. So that's roughly our plan from here. And in next video, we will keep talking about how to make further modifications here.